Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore some of the most fascinating places in the oceans. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. In the middle of the South Pacific, there is a mathematically calculated point, not discovered by an explorer, but found by an algorithm. That is the farthest place from any land in every direction. It is Point Nemo, the oceanic pole of inaccessibility. It sits 2,688 kilometers from the three nearest landmasses: Ducie Island to the north, Motu Nui, near Easter Island, to the northeast, and Mar Island, close to Antarctica, to the south. All of them are uninhabited. This means that within a radius of over 22 million square kilometers around the point, there is not a single person. The people closest to Point Nemo are often the astronauts aboard the International Space Station, which passes about 415 kilometers overhead. That extreme isolation has made it the planet's spacecraft graveyard. Since 1971, nearly 300 decommissioned spacecraft have been directed to fall in this region, including the Soviet space station Mir in 2001. The ISS itself is also planned to sink here when it is decommissioned, around 2031. Imagine drawing a circle on a map centered on Chicago with a radius large enough to reach Detroit, about 400 kilometers. Now imagine that within that entire circle, there is absolutely nothing but ocean. No anchored boat, no island, no reef breaking the surface. That mental exercise partially captures what the neighborhood of Point Nemo is like, except the actual scale is even more vast. Not 400, but 2,688 kilometers in every direction to the nearest land. The name Nemo comes from Latin and means no one. Croatian engineer Hrvoje Lukatila calculated the exact location of Point Nemo in 1992 with the help of computer programs and GPS satellites. There was no adventure of discovery, no risky expedition into unknown waters. Just precise calculations determining which point on the planet's ocean surface maximizes the distance to any piece of dry land. Point Nemo is located within the South Pacific Gyre, a rotating current that prevents nutrient-rich waters from entering. Ocean currents work like invisible conveyor belts, moving masses of water in circular patterns that can either distribute nutrients or cut them off. In this specific region, the gyre traps a nutrient-depleted central zone, preventing organic-rich material from continental coastlines or shallower ocean floors from reaching the surface. The direct consequence of this nutrient depletion is an almost complete absence of macroscopic life. Fish, whales, squid, organisms that depend on abundant food chains, rarely pass through these waters. Plankton exists in minimal quantities. The water column, from the surface down to the seafloor at approximately 3,700 meters deep, carries a biological density comparable to an arid land desert. Spacecraft resting on the ocean floor outnumber any sizable fauna. The spacecraft graveyard is a vast area in the Pacific Ocean, roughly centered on Point Nemo, where space agencies from around the world send their old and obsolete spacecraft. Since 1971, more than 260 spacecraft have been deorbited into this region, including satellites, space stations, and cargo vehicles. The controlled disposal process follows a precise protocol. Engineers calculate atmospheric re-entry trajectories months in advance, adjusting residual thrusters to guide the spacecraft toward Point Nemo. Most of the metal structure breaks apart in the heat of re-entry. Temperatures exceeding 1,600 degrees Celsius incinerate aluminum, plastic, and electronic components. Larger fragments, resistant enough to survive atmospheric ablation, impact the ocean within a defined zone, sinking to depths where they will never pose a danger. One of the most notable examples of spacecraft that ended up here is the Mir space station, the famous Soviet space station that was deorbited in 2001 after 15 years in space. Other examples include the Soviet-era Salyut station series and the unmanned cargo spacecraft that resupplied the International Space Station. The ISS, the orbital platform continuously inhabited since the year 2000, is home to the most curious human paradox in relation to Point Nemo. Astronauts aboard the ISS pass just 400 kilometers from this point when the orbit crosses the Pacific Ocean, which means that humans in space are closer to Point Nemo than anyone on Earth. The most inaccessible place on the planet has the sky as its nearest neighbor. In March 2024, British explorer Chris Brown led an expedition to the exact coordinates of the location. He faced a hurricane and rough seas to reach the point. Upon arriving, he dove into the cold waters, becoming possibly the first human being to swim at the most inaccessible point on the planet. The isolation is not only geographic, it is also atmospheric and climatic. Storms form and dissipate in this region without any land-based observer recording them. Waves over 10 meters high sweep the surface with no human witnesses. The average depth of the ocean floor in this zone exceeds 3,700 meters, ensuring that any object deposited there remains out of reach of conventional recovery technologies. Point Nemo exists as a mathematical certainty in an ocean that keeps its vastness intact, receiving technological relics in a silence that no sensor transmits back. To the east of Point Nemo, in the tropical seas of the Indian and Pacific Oceans, sailors have reported for centuries a phenomenon that no simple instrument detects and no conventional camera captures adequately. Stretches of ocean that glow a uniform white at night, across expanses of tens of thousands of square kilometers, for days or weeks at a time. A comprehensive database of Milky Sea sightings was published in 2025 as an important first step toward understanding the climatology of the phenomenon. The most widely accepted hypothesis is that colonies of bioluminescent bacteria associated with microalgae blooms produce this continuous, uniform glow, different from the pinpoint flashes of dinoflagellates. In 2019, the crew of the sailing vessel Ganesha crossed one of these events near Java and photographed the phenomenon for the first time from sea level. The exact mechanism that synchronizes billions of bacteria to glow together, covering areas visible from satellite, remains without a complete explanation. Bioluminescence is the ability of living organisms to produce light through internal chemical reactions. No heat, no combustion, no external electricity. Fireflies are the most familiar example. Luciferin, an organic molecule, reacts with oxygen in the presence of an enzyme called luciferase, releasing energy in the form of visible photons. In the ocean, this phenomenon is extraordinarily widespread. Various species of plankton, jellyfish, crustaceans, and fish produce their own light for communication, predation, or defense. So-called Milky Seas represent a radically different manifestation of this ability. The glow of Milky Seas is bright enough to read by and resembles the greenish-white glow of decorative glow-in-the-dark stars. It extends across ocean areas of up to 100,000 square kilometers and can be detected by satellites. To put that in perspective, 100,000 square kilometers is roughly the size of the entire state of Kentucky, lit up by microscopic organisms invisible to the naked eye individually. Milky Seas are a rare form of marine bioluminescence. Characterized by a steady, non-intermittent white-colored glow, they remain active for weeks. The most likely hypothesis is that the glow is produced by the luminous bacterium Vibrio harveyi. This bacterium is microscopic, individually invisible. To produce illumination detectable by satellite, trillions of them need to glow simultaneously, maintaining this collective behavior for weeks on end, synchronized by mechanisms still not fully understood. The transformation of milky seas from sailor's tale to scientifically treatable phenomenon began in the mid-2000s, when Stephen Miller, an atmospheric scientist at Colorado State University, realized that the new generation of meteorological satellites being launched carried sensors sensitive enough to detect very low levels of visible light at night. The day/night band sensor, designed to map urban lighting and capture lunar reflections in clouds, turned out to be capable of detecting the diffuse, steady glow of milky seas during nighttime passes on moonless nights. Between late July and early September 2019, low-light sensors detected a possible bioluminescent Milky Sea south of Java, Indonesia, covering more than 100,000 square kilometers. It was during this event that the crew of the sailing vessel Ganesha, casually navigating through the region, observed and recorded the phenomenon directly from sea level for the first time under scientifically documented conditions. In 2025, researchers published a comprehensive database of Milky Sea sightings, made up of first-hand observer accounts, historical records, and satellite data, representing the first important step toward understanding the climatology of the phenomenon and serving as a foundation for predictive algorithms. The archive compiled 400 years of records, bringing together logbooks, maritime communications, and orbital images into a single, searchable database. The database shows that sightings generally occur in the Arabian Sea and Southeast Asian waters, and are statistically linked to the Indian Ocean Dipole and El Niño. These climate connections suggest that Milky Seas are not random. They arise in response to specific oceanic and atmospheric conditions that can be monitored and eventually anticipated. Researchers still do not know what Milky Seas mean for the ecosystems where they occur. They could indicate either a healthy ecosystem or one out of balance. The bacteria suspected of producing them are known to negatively impact fish and crustaceans. The synchronization mechanism remains the biggest mystery. Bacteria communicate through chemical molecules that detect population density, a process called quorum sensing. When the concentration of bacteria exceeds a certain threshold, chemical signals trigger collective behaviors. In Milky Seas, this mechanism possibly coordinates trillions of organisms to simultaneously activate their light production, creating a bioluminescent field vast enough to be detected from space. At the bottom of the Black Sea, hidden under hundreds of meters of water, there is a river that flows with banks, a riverbed, rapids, and even waterfalls, and which was only confirmed in 2010. The Black Sea's underwater river is a current of particularly saline water that flows through the Bosphorus Strait and along the floor of the Black Sea. The discovery was announced on August 1, 2010, by scientists at the University of Leeds, and is the first of its kind identified in the world. The mechanism is physical. Salter, denser water from the Mediterranean enters through the Bosphorus and immediately sinks below the less saline water of the Black Sea, flowing along the bottom like a river within a river. It is 60 kilometers long, up to 1 kilometer wide, and 35 meters deep. It flows at more than 22,000 cubic meters of water per second, 10 times more powerful than the largest river in Europe. If it flowed on the surface, it would be the 6th largest river on the planet by volume. Density is the ratio of mass to volume of a substance. Salt water is denser than fresh water because dissolved sodium and chlorine ions add mass without proportionally increasing volume. When two volumes of water with different salinity levels meet, the salter one sinks below the less saline one, just like oil floats on water because it is less dense. This simple principle, scaled up to oceanic proportions, produces extraordinary consequences at the bottom of the Black Sea. The Black Sea has a positive water balance, resulting in a flow of 300 cubic kilometers of water per year through the Bosphorus and Dardanelles Straits into the Aegean Sea. Mediterranean waters flow into the Black Sea as part of a two-way water exchange. Black Sea water is cooler and less saline, floating above the warmer, salter waters coming in from the Mediterranean. The water entering the Black Sea through the Bosphorus Strait comes from the Mediterranean and has a much higher salinity. The Black Sea, in turn, receives a large volume of fresh water from continental rivers, resulting in lower salinity. This difference creates a density gradient. The Mediterranean water, salter and heavier, sinks upon entering the Black Sea. As it descends along the slope of the underwater terrain, it begins flowing as a bottom current, maintaining its structure and speed. The equipment responsible for the discovery was the AutoSub 3, an autonomous underwater vehicle approximately 7 meters long, developed by the Natural Environment Research Council in the United Kingdom. Programmed to operate without a direct connection to the surface, the submarine was sent to navigate just a few meters above the channel, collecting detailed data on speed and direction. It was this precise data that confirmed what sonar had suggested: not a static groove in the sediment, but an active, organized flow. What researchers found was a real river, with banks, floodplains, waterfalls, and a flow of 22,000 cubic meters of water per second, 350 times the volume of the Thames. The Thames, a classic British point of reference, carries approximately 65 cubic meters per second under normal conditions, a modest volume compared to what silently drains along the bottom of the Black Sea. Scientists at the University of Leeds estimate that this channel would be the sixth largest river in the world if it flowed on the surface. It transports more than 22,000 cubic meters of water per second at a speed of over 6 kilometers per hour, 10 times greater than the Rhine River, one of the largest rivers in Europe. One of the most remarkable discoveries involves the physics of water movement around the channel's bends. In surface rivers, water rotates in a specific direction due to the Coriolis force, but in this underwater river it spirals in the opposite direction. This unique behavior occurs due to extreme pressure and density differences in the deep. The Coriolis force, the effect of Earth's rotation on moving fluids, operates in reverse in this high-density, high-pressure environment, revealing that the usual physical laws bend under extreme conditions. The channel is approximately 6,000 years old, as ancient as the first urban civilizations of Mesopotamia. For millennia, it has patiently carved out its bed in the sediment, deepening its banks and creating a morphology identical to that of surface rivers, yet concealed under hundreds of meters of saline water. Sonar mapped this terrain for decades without anyone being able to confirm whether there was an actual flow. Only the AutoSub 3 settled the question. Underwater rivers with similar density dynamics likely exist in other oceanic regions where two water masses with different salinity levels meet near sloping underwater terrain. The Black Sea offered the perfect laboratory for identification and detailed study for one singular geographical reason. The Bosphorus Strait acts as a raised sill that forces Mediterranean water to plunge abruptly, initiating a structured bottom flow sustained by a permanent difference in density. The river runs, without rest and without a visible surface, along the floor of a sea that sailors have crossed for millennia without imagining the current flowing silently beneath their hulls. In the Denmark Strait, between Greenland and Iceland, lies the largest waterfall on the planet, and no tourist can visit it because it is completely submerged. The Denmark Strait Cataract is technically the largest in the world, with waters plunging 3,500 meters down. The waterfall itself is about 2,000 meters tall because it lands in a deep pool of cold water that occupies the rest of the descent. The mechanism is the same as the Black Sea's underwater river. Cold, dense water from the Nordic seas meets warmer water from the Irminger Sea. The cold water immediately sinks below and flows over the enormous drop in the ocean floor, creating a downward flow estimated at more than 5 million cubic meters per second. The tallest waterfall on land, Angel Falls in Venezuela, is 979 meters tall, 3 times shorter. Niagara Falls carries 2,000 times less water. On the surface, ships cross the strait without noticing a thing. Density determines how fluids behave when distinct masses meet. Colder water packs its molecules more tightly, making it heavier per unit of volume than warm water. When these two masses collide, the denser one simply slides underneath the lighter one, exactly like oil floats on water. In the Denmark Strait, this basic principle operates on an oceanic scale, producing consequences that reshape the circulation of the entire Atlantic. The drop is what makes the cataract hard to compare to anything on land. Angel Falls drops 980 meters. The Denmark Strait's drop surpasses that by more than 3 times. Even just the portion before the deep pool, before the cold water reaches the reservoir that occupies the rest of the descent, totals approximately 2,000 meters, still twice the height of Angel Falls. The Denmark Strait cataract plunges 3,505 meters from the Greenland Sea into the Irminger Sea, carrying approximately 5 million cubic meters of water per second, surpassing any waterfall on land. Angel Falls is 3 times shorter. Niagara Falls carries 2,000 times less water, even at peak flow. The cataract is as wide as the Denmark Strait itself, approximately 480 kilometers wide, and the ocean floor descends over a length of 500 to 600 kilometers. If you could visualize it, it would look like a relatively low-gradient ramp. There is no vertical cliff like you see in land waterfalls. It is a long, continuous slope whose drama lies in volume and depth, not in speed. As a result, the water descending the cataract moves at approximately 0.5 meters per second, much slower than the dramatic drop of Niagara Falls, which exceeds 30 meters per second. If someone were at the bottom, they probably wouldn't notice much happening at all. What happens in the Denmark Strait doesn't stay in the strait. This hidden waterfall is a crucial gear in Earth's climate machine, driving what scientists call the Atlantic Meridional Overturning Circulation, or AMOC, a kind of giant conveyor belt that moves heat around the planet. When cold, dense water plunges through the strait, it flows southward along the ocean floor, eventually reaching the southern hemisphere. The water from the cataract doesn't stay put once it reaches the ocean floor. It forms a massive current traveling southward, replacing warmer surface water that flows northward. The volume of water in this flow is equivalent to between 20 and 40 times the combined flow of every river that empties into the Atlantic. Between 17,500 and 11,500 years ago, when mammoths still roamed parts of the Earth, glaciers were sculpting the seafloor in ways that would change the planet. As the Ice Age ended and the glaciers retreated, they left behind a dramatic underwater landscape. A steep ridge now channels cold water from the Nordic seas downward toward the Irminger Sea. A ship could sail directly over the Denmark Strait cataract without ever noticing it. Satellites cannot detect it from space, and even divers at the surface would observe nothing unusual. The waterfall exists in a domain beyond direct human perception, detectable only by sophisticated scientific instruments. At the bottom of the ocean, along the mid-ocean ridges where tectonic plates pull apart, there are chimney-shaped structures that spew water at temperatures that melt metal. These are black smokers, hydrothermal vents that were discovered in 1977 in the Galapagos Islands and changed science's understanding of the limits of life. The temperature of black smoker fluid can reach 400 degrees Celsius or more, but it doesn't boil under the extreme pressure of the deep ocean. The black color comes from iron sulfides and other minerals that precipitate the moment the superheated fluid meets seawater at 2 degrees Celsius. within a matter of centimeters. More than 700 animal species are found exclusively at hydrothermal vents. None of them depend on sunlight. Bacteria and archaea convert heat, methane, and sulfur compounds into energy through chemosynthesis. If the sun were to disappear and photosynthesis were to stop, life at hydrothermal vents could continue for millennia. Tectonic plates are rigid fragments of Earth's crust that float on the heated mantle and move slowly, a few centimeters per year. Where two plates pull apart, magma rises from the depths, creating new oceanic crust. This process generates intense heat. Seawater seeps through cracks in the ocean floor, penetrating several kilometers until it reaches rock heated by magma. Superheated and chemically enriched, this water rises back up and is expelled through the chimneys. Black smokers are located along mid-ocean ridges, between 700 meters and more than 4,000 meters deep, in areas of high volcanic activity. These sites produce fluids at very high temperatures, reaching 410 degrees Celsius. Water doesn't boil at those depths because the extremely high pressure, equivalent to hundreds of Earth atmospheres, raises the boiling point well above 100 degrees Celsius. The fluid stays liquid even at temperatures that would melt lead. Black smokers are chimneys formed by iron sulfide deposits, which are black. White smokers, on the other hand, are chimneys formed by barium, calcium, and silicon deposits, which are white. The characteristic dark coloring arises from a violent thermal shock. Minerals dissolved in the superheated fluid precipitate instantly upon contact with ocean water at around 2 degrees Celsius, forming solid particles that create the visible dark smoke. Before the discovery of black smokers, all food chains were considered to be dependent, at their base, on photosynthesis and the sun. The deep ocean life known up to that point depended on the remains of dead photosynthetic plankton and larger animals that sank through the water column. The discovery of thriving ecosystems with no connection whatsoever to solar energy was one of the biggest revisions in 20th century biology. Microorganisms at hydrothermal vents, including bacteria and archaea, use the chemical soup expelled by the vents as an energy source instead of sunlight, in a process called chemosynthesis. These microbes are the foundation of the food web that sustains life in a diverse ecosystem that can include tube worms, shrimp, mussels, fish, crabs, and other organisms. Since then, more than 500 other hydrothermal vent sites have been located along the oceanic ridges that surround the tectonic plates of Earth's crust. Each newly discovered field brings species not yet cataloged, adapted to specific combinations of temperature, chemistry, and pressure. Since the initial discovery, hundreds of vents have been located throughout the global ocean, from the Arctic to Antarctica, with an estimated 800 animal species from vent sites and countless microbial species documented. The rate of discovery shows no signs of slowing down. Similar microorganisms have inspired theories that the most primitive ancestors of life may have originated in hydrothermal vent environments 4 billion years ago. If life emerged without sunlight on a primitive Earth, photosynthesis would have come later, not at the beginning of the planet's biological history. On Christmas Island, an Australian territory in the Indian Ocean, lives one of the largest populations of a single land animal concentrated in one place. More than 120 million red crabs, Gecarchoidea natalis *, inhabit the island's rainforest, existing exclusively here. Once a year, at the start of the rainy season, usually October or November, they all emerge at the same time. During the annual mass migration to the sea, millions of crabs surface simultaneously, blanketing the ground. Authorities shut down roads and set up detours. The exact timing and pace of the migration are determined by the phase of the moon. Red crabs always spawn before dawn, during the receding high tide of the last quarter moon. Each female releases up to 100,000 eggs into the ocean in a single night. The eggs hatch immediately upon contact with seawater, and the millions of larvae that emerge attract whale sharks and manta rays that gather offshore specifically for this annual feast. Synchronized animal migrations exist across many species around the planet. Wildebeest on the African savanna, monarch butterflies crossing North America, sardines in massive schools along the South African coast. None of them, however, concentrates such a volume of individuals of a single species in such a small territory as the red crab migration on Christmas Island, a 135 square kilometer rock lost in the Indian Ocean. Christmas Island is the only place on Earth where these famous bright red crabs are found. Official counts put the number at around 120 million, but local residents estimate it is at least double that. The migration begins with the first rain of the wet season, usually in October or November, though it can happen as late as December or January. Crabs all across the island abandon their burrows at the same time and begin marching toward the ocean to mate and spawn. The males lead and are joined by the females along the way. The exact timing and pace of the migration are determined by the phase of the moon. Red crabs always spawn before dawn, during the receding high tide of the last quarter moon. This lunar synchrony is not learned behavior or cultural. It is biological, hardwired into the nervous system of each individual over thousands of generations. The clock that governs them is the same one that regulates the tides and that sailors have relied on for millennia. Depending on when the first rains arrive and the time remaining to hit the ideal lunar quarter, the crabs may rush or move slowly, stopping to eat and drink along the way. If the lunar window closes entirely, some crabs skip the migration and wait for the following month. Each female can produce up to 100,000 eggs, which she carries in an abdominal pouch. When the moon reaches its last quarter, females loaded with eggs leave their burrows and gather at the shoreline, crowding into shaded patches above the waterline. In some areas, up to 100 crabs per square meter of beach or rock can be observed. When the high tide begins to recede before dawn, the crabs enter the sea and release their eggs, then return to the forest. The larvae go through several stages before transforming into juvenile crabs and leaving the water. Measuring about 5 millimeters, the tiny crabs begin marching inland, taking approximately 9 days to reach the safety of the plateau. There, they stay hidden in rocky outcrops and forest debris for the first 3 years of their lives. Millions of larvae are consumed by fish and filter feeders such as manta rays and the enormous whale sharks that visit Christmas Island's waters during the crab spawning season. After about a month in the ocean, the surviving larvae develop into shrimp-like animals called megalopas, which gather in pools near the shoreline for 1 to 2 days before transforming into small crabs and leaving the water. In most years, few or no baby crabs emerge from the sea, but once or twice a decade, a large number manage to survive, enough to sustain the island's large red crab population. The math is brutal: 120 million females, each with 100,000 eggs, produce 12 trillion larvae per cycle. Of those, the overwhelming majority perish. The species persists because the sheer numbers guarantee that, even with minimal survival rates, some always make it back. South of Japan, in a stretch of the Pacific Ocean between the Bonin Islands and Iwo Jima, lies a region known to Japanese sailors for centuries as Ma no Omi, the Sea of the Devil. The Western name is the Devil's Triangle, or Dragon's Triangle. Japanese maritime folklore is rich with stories of treacherous seas. Fishermen spoke of regions where dragons lurked beneath the surface, dragging vessels to the bottom. The name Ma no Omi has been used informally for generations to describe dangerous waters south of the Japanese archipelago. In 1952, the Japanese government sent a research vessel to investigate ship disappearances in the area. The ship Ko Maru No. 5, with 31 crew members, sank in the region. It was later discovered that an underwater volcano had exploded exactly when the vessel arrived at the location. The water became too hot, lost buoyancy, and the ship sank suddenly. The region has intense volcanic and seismic activity. Small islands in the area disappear, and new ones emerge as a result of this activity. The mysteries of the Devil's Triangle have geological explanations, but the geology, in this case, is genuinely extreme. There are 12 regions on the planet where maritime folklore has built up stories of unexplained disappearances, anomalous currents, and strange ocean behavior. The Bermuda Triangle in the North Atlantic is the most famous. The Devil's Triangle in the Western Pacific is its Japanese equivalent, with one crucial difference. While scientific investigations have revealed that the supposed mysteries of the Bermuda Triangle are largely exaggerated or made up, the phenomena of the Devil's Triangle have a genuine, documented geological basis. The Sea of the Devil is a loosely defined region in the Western Pacific Ocean, situated approximately 100 kilometers south of Tokyo, near the Izu Islands, extending toward the Bonin Islands and Iwo Jima. The region's name has its origins in ancient Chinese folklore, which described mythical dragons inhabiting the depths and causing ships to disappear. The region sits on the Pacific Ring of Fire, one of the most geologically unstable places on Earth. Underwater volcanoes erupt without warning. Earthquakes shake the ocean floor. Massive storms appear out of nowhere. Entire islands have formed and disappeared in the region. This behavior of the ocean floor is not a metaphor. It is recorded in modern geological and cartographic data. The 1952 to 1953 eruption of the Myojinsho volcano is a prime example of this risk, with explosive activity that generated tsunamis up to 2 meters high and scattered volcanic debris across the ocean surface. These eruptions fragmented shallow rock domes, ejecting dense pyroclastic fragments that sank rapidly while pumice stones floated, creating dangerous obstacles for vessels. The Ko Maru No. 5, with a crew of 31, was sent by Japan's Hydrographic Office to survey the area around the Bonin Islands. It sank on September 24, 1952, with all crew members lost. It was discovered that an underwater volcano exploded exactly when the ship arrived at the location. The water became too hot, lost buoyancy, and the ship sank suddenly. The crew had no chance to escape. Scientific studies point out that the ocean floor in the region contains methane hydrates. When the hydrated methane gas explodes, bubbles form on the water's surface. These gas eruptions can disrupt buoyancy and easily sink a ship without leaving any trace of wreckage. This mechanism, combined with direct volcanic eruptions, explains disappearances that for decades were attributed to the supernatural. It is quite characteristic of the Devil's Triangle that small islands frequently disappear and new ones emerge, the result of both volcanic activity and seismic movements. Islands recorded on nautical charts cease to exist. Others appear where there was only open ocean. Mapping this region is a permanently unfinished task. American writer Charles Berlitz popularized the region in the West in 1989, making widely exaggerated claims about the number of losses and the circumstances of the disappearances. Later researchers demonstrated that many of the shipwrecks attributed to the mystery occurred outside the alleged boundaries of the triangle or had documented causes. The real core of the phenomena, however, persists. The geology of the region is exceptionally violent, and sailors without modern instruments had legitimate reasons to fear those waters. The activity that sank the Ko Maru No. 5 in 1952 was not exceptional for the Devil's Triangle. It is the geological norm of the region. The conqueror Kublai Khan attempted to invade Japan in 1274 and again in 1281. In both attempts, He lost his ships and tens of thousands of crew members in this triangular area, supposedly due to typhoons. The Japanese believed that God had sent the typhoons to save them from their enemies. The region sits on one of the most active subduction zones in the Western Pacific, where the ocean floor produces earthquakes, tsunamis, and volcanic eruptions on a regular basis. The islands that appear and disappear are not legend. They are underwater seamounts that temporarily emerge during eruptions and then sink back down. The mystery of the Devil's Triangle is, to a large extent, the predictable behavior of a geologically violent zone that sailors of the past had no instruments to understand. Kublai Khan ruled the largest contiguous empire in human history. The grandson of Genghis Khan, he had conquered China, subjugated Korea, and sent armies to virtually every corner of Asia. Japan was the only territory that refused to acknowledge his sovereignty. Twice he mounted naval invasions on an unprecedented scale to subdue the Japanese islands. Twice the ocean responded with meteorological violence that wiped out all of the Mongols' numerical superiority. The first invasion force that attacked Japan in the fall of 1274 comprised around 30,000 to 40,000 men and an estimated 500 to 900 vessels. The typhoon struck while the ships were anchored in Hakata Bay, sinking about a third of them. An estimated 13,000 of Kublai's men drowned. The second Mongol fleet was far larger, made up of two separate forces with a combined contingent of 4,400 vessels and around 140,000 soldiers and sailors. On August 15, 1281, as they were preparing to attack Japanese forces, a massive typhoon struck, destroying the Mongol fleet and once again foiling the invasion attempt. The invasion forces suffered tremendous casualties, with at least half of the Mongol warriors drowning and all but a few hundred vessels lost during the storm. The Japanese interpreted both storms as divine intervention, sacred winds sent by the gods to protect the islands. The word that described these winds, kamikaze, would centuries later be repurposed to name suicide pilots in war. In 2014, geologist John Woodruff of the University of Massachusetts discovered physical evidence corroborating the historical accounts. By analyzing sediment cores from lake beds near Hakata Bay, he found distinct deposits corresponding to major typhoons. Two layers dated to the late 13th century, corresponding to 1274 and 1281. The frequency of storm deposits is higher in the 13th century, and the two most significant deposits are consistent with the timing of the legendary kamikaze typhoons. The cause of the storms appears to be linked to more frequent El Niño activity during the period of the Mongol invasions. The region, which encompasses parts of the Isobonin volcanic arc in the Western Pacific, is prone to underwater volcanic eruptions that pose significant navigational hazards. This instability has not diminished since the 13th century. It is structural, stemming from the region's position over one of the most active subduction zones on the planet, where the Pacific Plate dives beneath the Eurasian Plate, generating enough pressure to fuel volcanoes, earthquakes, and tsunamis indefinitely. The difference between the 13th century and the 21st century is instrumental, not geological. Satellites monitor typhoons as they form. Seismographs record underwater tremors before waves reach the surface. Radar detects volcanic eruptions as they happen. Medieval sailors navigated the same ocean with stars and accumulated experience. And when the seafloor exploded beneath their hulls, or winds of 200 kilometers per hour shattered their timber, the only language available to describe the event was that of dragons and gods. Point Nemo, the Milky Sea, the Black Sea's underwater river, the Denmark Strait Cataract, the Black Smokers, the Christmas Island crabs, and the Devil's Triangle are all places on the same planet, separated by thousands of kilometers of ocean, connected by the same continuous body of water. The Black Sea River flows into the Mediterranean, which feeds the Atlantic, whose waterfall at the Denmark Strait drives the global thermohaline circulation, which distributes heat and carbon to all the oceans, including the South Pacific, where Point Nemo lies. The black smokers on the floor of the mid-ocean ridges sustain ecosystems that depend on none of these systems, only on the heat from Earth's interior. And in the waters around Christmas Island, whale sharks rise every year to feed on 100 million crab larvae released in a single night of the waning moon. Thermohaline circulation is the technical name for the system of deep ocean currents driven by differences in temperature and salinity, the same mechanisms that create the Black Sea River and the Denmark Strait waterfall. Thermo refers to heat, haline to salt. When surface water cools and increases in salinity through evaporation, it becomes dense enough to sink, initiating currents that travel along the ocean floor for decades before resurfacing in other regions. The Denmark Strait waterfall is one of the main pumps of this system. The water from the cataract doesn't stay put once it reaches the ocean floor. It forms a massive current traveling southward, replacing warmer surface water that flows northward. The volume of water in this flow is equivalent to between 20 and 40 times the combined flow of every river that empties into the Atlantic. This flow carries dissolved oxygen to abyssal depths, fertilizes marine ecosystems, and regulates temperatures across every continent washed by the Atlantic. The Black Sea's underwater river, in turn, feeds the Mediterranean with dense, mineral-rich water that eventually contributes to the Atlantic system. Each apparently isolated phenomenon connects to the others through the physical continuity of the ocean. The same body of water that bathes Antarctica circulates through the Indian Ocean and resurfaces in the North Pacific. Point Nemo sits at the center of an ocean gyre that is itself a product of this global circulation. The black smokers represent the only truly independent system in this network. While all the other phenomena depend to some degree on solar energy, which heats the surface, evaporates water, generates winds and currents, the black smokers are powered by the geothermal heat of Earth's interior. Microorganisms at hydrothermal chimneys oxidize hydrogen sulfide or methane, and larger animals harvest microbial energy through grazing, filtering, or symbiosis. This cycle has existed for as long as tectonic plates have existed, independent of any star. The Milky Sea, however, connects both worlds. The bacteria that likely produce it depend on ocean nutrients distributed by thermohaline circulation. The climate patterns that determine when and where it appears, the Indian Ocean Dipole and El Niño, are themselves regulated by the heat transported by these deep currents. The gyre that impoverishes Point Nemo enriches other regions. The same system that makes one area seem barren feeds, at other points, biological explosions that light up entire oceans. Christmas Island completes the biological circuit. Millions of crab larvae are consumed by fish and filter feeders, such as manta rays and whale sharks, that visit the island's waters during spawning season. Whale sharks, the largest fish on the planet, migrate through the Indian Ocean following temperature gradients and plankton concentrations, patterns determined by the same ocean circulation that drives the Denmark Strait waterfall and the Black Sea River. The crab's calendar and the current's calendar obey the same clock. Islands in the Devil's Triangle suddenly disappear, while new ones emerge at the same rate, as a result of seismic activity. The ocean floor is not static, it is geologically active, continuously reshaped by plate tectonics, volcanic eruptions, and currents that carry sediment for thousands of kilometers. The Black Sea's underwater river has existed for 7,500 years, since the Bosphorus developed its two-way flow at depth. The Denmark Strait waterfall operated throughout the last ice age. Black smokers appear and disappear as the ocean floor shifts. Point Nemo changed coordinates when LOCATILA recalculated its position in 2022 with more precise data. The most remote place on Earth moved a few kilometers, and the Milky Seas, recorded by sailors for centuries, received their first comprehensive scientific database only in 2025. The ocean that covers 71% of the planet still produces new places, and still reveals, year after year, places that were there all along without anyone being able to explain them. Mapping the planet seemed, for a moment, like a finished task. Earth observation satellites cover every square kilometer of surface with enough resolution to identify individual structures. Global positioning systems locate any point with meter-level precision. Digital nautical charts update in real time with data on tides, currents, and hazards. And yet the ocean, which covers more than 2/3 of the planet's surface, keeps producing phenomena that appeared on no chart. In 2022, LOCATILA recalculated the coordinates of Point Nemo using data from OpenStreetMap and Google Maps to compare the results with the coordinates he had originally calculated using data from the digital chart of the world. The most remote point on Earth had shifted, not because the ocean changed, but because the data got more precise. What seemed fixed was an approximation. Reality is slightly different from the best previous estimate. It is quite characteristic of the Devil's Triangle that small islands frequently disappear and new ones emerge, the result of both volcanic activity and seismic movements. Islands that appear on nautical charts from one decade cease to exist in the next. The instability is not the exception. It is the normal state of a geologically alive region, where the ocean floor continuously rebuilds itself. In 2025, researchers published a comprehensive database of Milky Sea sightings, the first important step toward understanding the climatology of the phenomenon. 400 years of sailors' records had been waiting for systematic compilation. The phenomenon existed. What was missing was the archive. Science revealed that what seemed supernatural, oceans glowing from horizon to horizon for weeks, has an identifiable biological cause and a traceable climate pattern. Microorganisms similar to those of black smokers inspired theories that the most primitive ancestors of life may have originated in hydrothermal vent environments 4 billion years ago. If that is true, life on Earth began in a place exactly like the ones described here. Without sunlight, without photosynthesis, powered by the heat of the planet's interior, in an ocean that no map could have recorded because there was no one yet to draw it. Since the initial discovery of black smokers, hundreds of hydrothermal vents have been located throughout the global ocean, from the Arctic to Antarctica, and the rate of discovery shows no signs of slowing down. Every new expedition finds hydrothermal fields in locations where no theory had predicted their existence. The ocean has not run out of secrets. It continuously produces new ones, at depths that earlier instruments could not reach, and in regions that no expedition had ever visited. Point Nemo receives spacecraft because it is empty and remote. The Milky Sea glows because trillions of bacteria respond to a signal still not fully understood. The Denmark Strait waterfall regulates the climate of entire continents without anyone on the surface noticing its movement. The black smokers sustain life that challenges the very definition of what conditions are necessary for it to exist. The Black Sea River has been running for millennia beneath vessels that had no idea it was there. The Christmas Island crabs follow a lunar clock that predates any human calendar. The Devil's Triangle has sunk entire fleets with phenomena that modern geology describes with precision, but which remain, on a human scale, violently unpredictable. The ocean has been the same system since the beginning. What changes is the instrument you use to look at it.